Welcome to the fascinating and complex world of modern wind turbine manufacturing. Here, engineering precision meets industrial scale in the creation of massive machines designed to harness the power of the wind and convert it into clean electrical energy that powers our world. Today, we will take you on an extraordinary journey through the complete manufacturing process of a modern wind turbine. A journey that spans from raw materials arriving at the factory all the way to a finished turbine ready to generate electricity for decades. This is not a simple process. Modern wind turbines are among the most sophisticated machines manufactured today, combining advanced materials, intricate mechanics, and complex electronics to create power generation systems of remarkable capability. Watch as massive towers are fabricated from steel, rising hundreds of meters into the sky. Observe the manufacturing of enormous rotor blades that will span the width of a football field, crafted from advanced composite materials. Witness the assembly of the nacelle, the heart of the turbine, where the gearbox, generator, and control systems work in perfect coordination. This is the story of how we create machines that capture invisible wind energy and transform it into tangible electrical power. This is the story of precision engineering at an industrial scale. This is the story of human innovation creating the sustainable energy infrastructure that will power future generations. So settle in, relax, and prepare to observe one of the most impressive manufacturing achievements of our time unfold in meticulous detail, step by careful step. Before any turbine is manufactured, it must first exist as a concept in the minds of engineers, then be carefully designed and refined through computational analysis. The design phase is extraordinarily complex and critical. Wind turbine design begins with determining the turbine specifications. How large should it be? Modern turbines range from smaller utility-scale machines producing a few megawatts to massive offshore turbines exceeding 15 megawatts of capacity. The size determines how many blades, their dimensions, the tower height, and every other specification of the machine. The design must balance multiple competing factors. Larger turbines capture more wind energy and produce more electricity, but they are more expensive to manufacture and install. They require stronger towers and more sophisticated foundations. The blades must withstand more stress. Every design parameter is a trade-off between efficiency, cost, and practical construction limitations. Engineers using sophisticated computer software create detailed three-dimensional models of the turbine. The models show every component: the tower structure, the nacelle containing the generating equipment, the rotor assembly with its blades, the control systems, and the electrical connections. The software allows engineers to examine the design from any angle, checking for interference between components, verifying that all parts fit together correctly. Watch as engineers work at their computer stations, manipulating the three-dimensional model with mouse movements. They rotate the model, examining it from different perspectives. They zoom in on critical connections, checking that components fit together without gaps or misalignment. They adjust parameters, perhaps changing blade length by 5 centimeters, and observe how this change affects the overall design. Aerodynamic analysis is performed using computational fluid dynamics, CFD software that simulates airflow around the turbine blades. The software models how wind strikes the blades at different angles and speeds. It calculates the lift and drag forces that the blades will experience. This analysis is critical because the blade design must maximize the extraction of wind energy while minimizing stresses on the turbine structure. Structural analysis determines how the turbine will respond to the forces it will experience. Wind forces on the blades push the entire rotor, creating tremendous stress on the tower. The tower must be strong enough to support the rotor weight and resist wind forces without excessive deformation. Structural analysis calculates stresses in every component and verifies that no component will fail or deform excessively. Fatigue analysis is performed because the turbine will experience billions of stress cycles during its operational lifetime. Wind gusts cause the turbine to sway slightly. The rotor rotates at perhaps 15 revolutions per minute, but each rotation causes stress cycles in the structure. After 20 or 30 years of operation, the cumulative effect of billions of stress cycles could cause failure if components are not properly designed. Fatigue analysis ensures that all components can withstand this long-term stress cycling. The gearbox design is critical. Wind turbines typically rotate at relatively low speeds, perhaps 15 revolutions per minute, but electrical generators produce electricity efficiently at much higher speeds, perhaps 1,500 or 1,800 revolutions per minute. The gearbox increases the rotational speed from the low-speed rotor shaft to the high-speed generator shaft. The gearbox must be efficient, losing as little energy as possible to friction and heat. The design of gear teeth, bearing arrangements, and lubrication systems is highly engineered and critical to turbine efficiency. The generator must be selected or designed. Modern wind turbines may use traditional synchronous generators or permanent magnet generators depending on the design. The generator must produce electrical power at the correct voltage and frequency. In onshore grids, this is typically 690 volts or higher, with a frequency of 50 or 60 Hz matching the power grid frequency. The control system design is equally important as the mechanical design. Modern wind turbines are highly automated, with computerized control systems that continuously monitor turbine performance and adjust blade pitch angle to optimize energy capture. When wind speeds become excessive, the control system turns the blades to reduce their angle of attack, preventing damage to the turbine. The control algorithms must be robust and tested extensively because they are critical to safe operation and maximum efficiency. Material selection is a crucial design decision. The rotor blades must be lightweight yet strong. For this reason, they are manufactured from composite materials, fiberglass or carbon fiber embedded in epoxy resin. These materials provide the strength-to-weight ratio required. Aluminum or fiberglass is used for some components, but steel and concrete are used for the heavy tower structure. Different grades and types of steel are selected for different components. The tower requires steel that is strong but also ductile, capable of deforming without breaking if subjected to extreme loads. The bearing housings and gearbox casings require steel that is both strong and wear-resistant. The fasteners, bolts, nuts, and pins require specially hardened steel with precise properties. Composite materials require careful selection of fiberglass or carbon fiber reinforcement and the resin system. Different resin systems have different properties. Some cure quickly, others have lower heat generation during curing. The fiber orientation must be carefully planned to ensure the blade has proper strength in all directions it will experience loads. The design process includes creating detailed engineering drawings showing every component with all necessary dimensions, tolerances, and specifications. These drawings become the blueprints from which the manufacturing process will proceed. Every dimension is specified to the precision needed for that component. Some components require tolerance of plus or minus 1 millimeter. Others have looser tolerances. Material specifications are detailed in the design documentation. Steel type and grade are specified by designation. Fastener grades and finishes are specified. Composite material layup schedules are documented, showing exactly how many plies of fiberglass at what angles will be used in different parts of each blade. The design phase concludes with design review meetings where the entire design is presented to an engineering team who examine it for completeness, accuracy, and manufacturability. Questions are raised and answered. Potential issues are identified and addressed before manufacturing begins. The design is refined and optimized. Only after thorough review is the design finalized and authorized for manufacturing. The tower of a wind turbine is one of the largest components, standing perhaps 80 to 120 meters tall, yet assembled from cylindrical sections that are manufactured one at a time. Tower manufacturing is one of the first phases of turbine manufacturing because towers require the longest lead time and are the most substantial component. Steel coils arrive at the manufacturing facility. These coils, each weighing many tons, contain flat steel sheet from which tower sections will be formed. The steel has been manufactured by a steel mill in the specified grade, thickness, and width. The coils are stored in the factory yard, awaiting their turn to be processed. The steel is fed into a rolling mill. This is a remarkable machine consisting of heavy rollers mounted in a frame. The steel sheet passes through the rollers, which curve the steel into a cylindrical shape. The rollers gradually increase the curvature, and the steel begins to form into a circular cross-section. Watch the rolling process in detail. The flat steel sheet enters the mill and the rollers touch it lightly. The rollers are spaced vertically, and as they rotate, they curve the steel. The sheet passes through the rollers several times, each pass increasing the curvature. The steel gradually transforms from flat to slightly curved to more curved to finally forming an almost complete cylinder. The process continues, the sheet passing through the rollers repeatedly, the curvature increasing with each pass. As the curvature becomes more pronounced, the edges of the sheet are brought closer together. By the end of the rolling process, the edges are nearly touching, forming a nearly closed cylinder. The edges now must be joined together. The edges are beveled, cut at an angle so that they can be welded together. A submerged arc welding machine performs the weld that closes the cylinder. The machine positions itself at the joint between the two edges. The welding arc ignites under the surface of a flux material that protects the weld from atmospheric contamination. The welding head moves along the length of the joint, depositing metal that fuses the two edges together into a single piece. The weld is performed from both the inside and outside of the cylinder to ensure full strength. The welding is done in a controlled manner with the welding parameters, voltage, current, and travel speed precisely adjusted for optimal weld quality. The machine moves at a steady pace, creating a continuous bead of weld metal along the joint. After welding, the newly formed cylinder is subjected to stress relief. The welding process creates residual stresses in the steel around the weld joint. These stresses could cause the tower section to warp or fail prematurely if not relieved. The cylinder is heated in an oven to approximately 600 to 700 degrees Celsius and held at that temperature for several hours. This allows the steel to relax and relieve the internal stresses. The cylinder is then cooled slowly and carefully to prevent new stresses from forming. The tower section is transported through the facility to the machining area. Large machine tools will now perform precision work on the ends of the cylinder. These machines will cut the inside and outside surfaces of the ends to precise dimensions, and they will bore holes that will be used to bolt tower sections together. Watch as the section enters a massive horizontal boring mill. This machine has a large table capable of supporting the entire cylinder. The cylinder is positioned and clamped onto the table. The machine has rotary cutting tools that will bore holes and machine the surfaces. The cutting tools rotate at high speed. The machine table slowly advances the workpiece toward the cutting tools. The tools bite into the steel, removing chips and shavings. The cutting tools must be fed at the right speed and advance rate to achieve the proper surface finish and tool life. Too fast and the tool overheats. Too slow and the operation becomes inefficient. Multiple holes are drilled around the circumference of the cylinder ends. These holes will align with corresponding holes on adjacent tower sections or on the base. When the turbine is assembled, large bolts will pass through these holes, fastening the sections together. The holes must be precisely positioned and the correct diameter. Tolerance is tight, perhaps plus or minus 1 or 2 millimeters, to ensure that when sections are bolted together, they align properly. The inside surface of the cylinder is also machined to provide a smooth, precise surface. This is important for manufacturing quality and for proper functioning of components that will be inserted into the tower. The machining removes any scale or irregularities left from the rolling and welding process. The exterior surface is also inspected and prepared. Any surface irregularities are noted. Dents or gouges are evaluated to determine if they are acceptable or if they require repair. Welded surfaces are ground smooth to ensure they meet surface finish specifications. Quality control measurements are taken. The wall thickness of the cylinder is measured at multiple locations to verify it meets the specification. The dimensional measurements of the holes are verified. The straightness and roundness of the cylinder are checked using precision instruments. Multiple tower sections are manufactured through this same process. A large turbine might require 4 or 5 tower sections, each perhaps 30 to 40 meters long. Each section is manufactured independently, then later they will be bolted together to form the complete tower. Some sections are thicker than others. The base of the tower must be thicker and stronger because it must support the weight of the entire turbine and resist the bending forces created by wind. Higher sections, which must support less weight, can be slightly thinner. The completed tower sections are stored at the factory or transported to the assembly facility where they will later be joined with the other turbine components. The manufacturing of tower sections is a continuous process. While some sections are being rolled and welded, others are being machined and inspected. The factory operates in a coordinated flow, with each section proceeding through its manufacturing steps in sequence. Rotor blades are the most visible components of a wind turbine, and their manufacturing is one of the most sophisticated processes in the entire turbine manufacturing system. Modern wind turbine blades are among the largest composite structures manufactured today. The manufacturing of rotor blades begins with the creation of molds. Large composite structures like wind turbine blades are manufactured by laying up multiple layers of composite material, fiberglass or carbon fiber fabric embedded in epoxy resin, into a mold that defines the final blade shape. The mold is extremely large, possibly exceeding the dimensions of the final blade itself by a small margin to allow for material shrinkage during curing. The mold is positioned in the manufacturing area. The mold for a large blade might be over 50 meters long and require several people to handle. The interior surface of the mold is carefully prepared. It is cleaned and treated with a release agent, a substance that prevents the cured composite from sticking to the mold, allowing the finished blade to be removed after curing. Workers begin the layup process. They carefully position the first layer of fiberglass or carbon fiber fabric into the mold. This fabric is dry material. It will be impregnated with resin as the layup process progresses. The fabric is smoothed into place, ensuring it conforms to the contours of the mold without wrinkles or bubbles. The resin is prepared. Two-part epoxy resin is the typical choice for wind turbine blades. The resin components are mixed in controlled proportions. The ratio must be precise. Deviation from the correct ratio will affect curing time and the final material properties. The resin is typically applied using a spray gun or by rolling, distributing it evenly over the dry fiber fabric. Watch the resin application in detail. A worker holds the spray gun, directing a fine mist of resin over the fabric layer. The resin soaks into the fabric, penetrating to ensure that all fibers are properly coated. The worker moves the gun in a controlled pattern, ensuring even application. The spray must be at the right angle and distance to provide proper coverage without excessive overspray or waste. As the resin is applied, it begins to bond with the fibers. The fibers become saturated with resin, transforming from dry material into a wet composite that begins to take on the shape of the mold. The worker uses rollers to compress the layer, removing air bubbles and ensuring that all fibers are fully impregnated with resin. The next layer of fabric is positioned over the first layer. The orientation of the fibers in this layer may be different from the first layer. This is critical for blade strength. Fibers oriented one direction provide strength in that direction. A blade must be strong in multiple directions, along its length, resisting bending, perpendicular to its length, resisting shear forces, and resisting torsional forces that would twist the blade. By orienting fiber layers in different directions, engineers create a structure that is strong in all required directions. The resin is applied to the second layer. The saturation and compression process is repeated. Additional layers are added one by one. The layup process is methodical, repetitive, and requires considerable skill. Workers must be careful to apply resin uniformly, compress each layer thoroughly, and position each successive layer accurately. As the layup builds up, the thickness of the composite structure increases. A finished blade might have dozens of layers, ranging from thin outer skins to thick structural layers, creating a sandwich structure with foam core material providing stiffness without excessive weight. Some blade designs include structural reinforcements, spar caps made of carbon fiber or high-strength fiberglass positioned strategically to provide maximum strength where it is most needed. These spar caps run the length of the blade, providing the primary structural strength that allows the blade to resist the enormous bending forces it will experience when the rotor is turning. The layup process continues until the complete structure is built up to the design thickness. The completed wet composite in the mold is allowed to cure. The curing process is temperature controlled. Infrared heaters or ovens may be used to maintain temperature at the optimal range for the epoxy resin curing reaction. The curing typically takes many hours, perhaps 12 to 24 hours or more, depending on the resin system and temperature. During curing, the epoxy resin undergoes a chemical reaction, transforming from a liquid state into a solid plastic. The fiberglass fibers remain embedded in the hardened resin, creating a composite structure with the strength characteristics designed into it. Watch as the blade cures. The curing is not visible from the outside, but inside the mold, the chemical reaction is proceeding. The resin gradually hardens. After several hours, the resin is solid enough to handle. After a full day or more, the resin is fully cured and has reached final strength. Once the resin is fully cured, the blade is removed from the mold. This is a critical operation because the blade is large and delicate. The blade is supported by mechanical equipment, lifting straps and supports that prevent it from bending excessively or being damaged. The blade is carefully lifted from the mold and placed on supporting racks. The demolding process can be tricky. If the blade adheres to the mold and cannot be easily removed, mechanical assistance may be needed. Small demolding machines using air pressure or hydraulic pressure can help separate the blade from the mold without damage. Once removed from the mold, the blade is inspected. The surface is examined for defects, wrinkles, bubbles, or other imperfections. Small imperfections may be acceptable if they do not affect blade performance. Larger defects might require repair. Some blades with significant defects might need to be scrapped. The blade surface is trimmed. Excess resin and fiber around the edges is cut away. The blade is sanded and finished to remove irregularities and provide proper aerodynamic shape. This finishing process might take several workers several days for a large blade. The interior of the blade is also inspected if possible. Some blade designs include access ports allowing inspection of the internal structure. Ultrasonic scanning might be performed to verify that the composite structure is free of delaminations, separations between layers that would weaken the blade. The finished blade is painted or coated with protective finish. The white color typical of modern wind turbine blades provides aesthetic appeal and helps reflect heat from the sun. The protective coating also provides weather protection, preventing UV degradation of the composite material. The completed blade is transported to storage or to the assembly facility. Multiple blades are manufactured for each turbine, typically 3 blades per rotor, so manufacturing processes produce many blades continuously. The nacelle is the pod-shaped structure mounted at the top of the tower. It contains the gearbox, generator, and all the electrical and mechanical systems that convert the rotational energy of the rotor into electrical power. The nacelle is one of the most complex parts of the turbine to manufacture. The gearbox is manufactured in a specialized facility dedicated to gear manufacturing. The gearbox is a complex piece of machinery designed to increase the rotational speed from the slow-speed input shaft, rotating at perhaps 15 revolutions per minute, to the high-speed output shaft rotating at perhaps 1,500 revolutions per minute. The gearbox typically consists of multiple stages. The first stage might be a planetary gear arrangement, where a ring gear surrounds a smaller gear, with multiple planet gears positioned between them. This arrangement provides high torque multiplication in a compact design. Subsequent stages provide additional speed multiplication, each stage reducing the torque while increasing the speed. The gearbox housing is manufactured from ductile iron, a material that combines strength with the ability to absorb the vibration and shock that gear teeth generate. The housing is cast in large molds, with the material poured as liquid into the mold and allowed to cool. The casting is then machined to precise dimensions to create the surfaces where bearings and gears will be mounted. Individual gears are manufactured from specialized steel that is hardened to withstand the contact stresses between gear teeth. The gears are typically manufactured through a multi-step process. Steel blanks are cut from bar stock or are formed through forging. The blanks are machined to remove excess material. Then the gear teeth are cut using specialized gear cutting machines that precisely shape each tooth. The gear teeth must be precisely shaped. The tooth profile, the curved surface of each tooth, is critical to the gearbox's efficiency and longevity. The tooth spacing must be precise, with each tooth equally spaced around the gear. After cutting, the gears are hardened through heat treatment, heating to high temperature and rapid cooling, to develop the hardness necessary to resist the enormous contact pressures that occur when teeth mesh. Some gears are ground after hardening to achieve even higher precision. This precision grinding removes minute amounts of material from the tooth surfaces, creating a surface finish that is smoother and more precise than cutting alone can achieve. The geared teeth are now ready to mesh together with minimal backlash and maximum efficiency. The gearbox assembly brings together the housing, gears, bearings, and shafts into a complete system. Bearings are installed in the housing to support the rotating shafts. The bearings must be precision components capable of supporting the enormous radial and thrust loads generated during operation. The bearings are carefully pressed into position with controlled force to ensure they are fully seated without damage. Seals are installed around the shafts where they pass through the housing. These seals prevent lubricating oil from leaking out and prevent contamination from entering. Proper sealing is critical because the gearbox must maintain its lubricating oil throughout years of operation. The gearbox is filled with specialized lubricating oil. This is not ordinary motor oil. Gear oil contains additives that modify its viscosity and provide protection against wear and oxidation. The oil viscosity must be correct for the intended operating temperature range. The oil is carefully measured and poured into the gearbox through a fill opening. A cooling system is integrated into the gearbox or mounted on the outside. The gearbox generates considerable heat through friction as gears mesh and oil is sheared. The cooling system uses oil pumps and coolers to circulate the oil, rejecting heat to the surrounding air or to a water cooling system. Temperature monitoring systems track the gearbox temperature, alerting operators if temperature exceeds design limits. The generator is manufactured using conventional electric machine manufacturing techniques. The generator may be a synchronous machine or an induction machine, depending on the turbine design. The stator, the stationary part of the generator, consists of stacked laminations of electrical steel, with coils of wire wound in slots in the steel. The rotor, the rotating part, consists of permanent magnets or wound field coils, depending on the design. The stator windings are precision work. The coils must be wound with the correct number of turns, and they must be positioned in the correct slots. The windings are insulated with electrical insulation material, protecting them from each other and from the machine frame. Multiple coils are connected together in a specific pattern that determines the electrical characteristics of the machine. Watch the winding process. A worker positions the first coil in the stator slot, then carefully inserts the leads of the coil into adjacent slots. The coil is held in place by wedges or by the pressure of adjacent coils. The next coil is positioned in the next slot, its leads routed through the appropriate adjacent slots. Coil after coil is positioned until all coils are in place. The rotor laminations are stacked and keyed to the rotor shaft. If the rotor uses permanent magnets, the magnets are glued in precise positions on the rotor surface. The rotor is then balanced to ensure smooth rotation with minimal vibration. The completed stator and rotor are assembled together, creating the complete generator. The rotor is inserted into the stator with precision alignment. Bearings in the generator frame support the rotor shaft. The complete assembly is tested to verify electrical performance. The generator is spun by an external drive, and the electrical output is measured to verify it meets specifications. The control system electronics are manufactured and assembled separately. Control modules contain microprocessors, power electronics and sensory equipment. The components are soldered onto printed circuit boards, creating the electronic control systems that will monitor turbine performance and adjust blade pitch to optimize energy capture. The converter electronics, power electronics that convert the variable frequency electrical power from the generator into the fixed frequency power required by the grid, are manufactured as a separate module. The converter must handle the full power output of the turbine, perhaps 5 to 15 megawatts, so the components must be large and capable of handling this enormous power transfer. Large semiconductor switches control the power flow, converting and conditioning it for grid injection. All these components, the gearbox, generator, control electronics, and converter, are transported to the Nacelle Assembly facility where they will be assembled together. The Nacelle Assembly brings together all the mechanical and electrical components of the turbine into the main operational unit. This assembly is performed in a large assembly facility where specialized fixtures and tooling support the work. The nacelle frame, a steel structure designed to house and support all the components, is positioned in the assembly jig. The frame is a strong structure, capable of withstanding the loads that will be transmitted to it when the rotor is turning. The frame structure creates mounting points for all the components. The gearbox is the first major component positioned into the nacelle. The gearbox is lifted by crane and positioned carefully into its mounting location on the nacelle frame. Alignment is critical. The gearbox must be positioned precisely so that the input and output shafts will be coaxial with the rotor and generator respectively. Specialized alignment fixtures verify that the positioning is correct. Once the gearbox is properly positioned, it is bolted to the nacelle frame using large bolts that are tightened to precise specifications. The bolts must be tight enough to securely mount the gearbox, but over-tightening can distort the gearbox housing or break the bolts. Torque wrenches ensure the bolts are tightened to exactly the correct tension. The generator is positioned next. The generator must be aligned with the gearbox output shaft so that the two can be coupled together. A flexible coupling joins the two, allowing for minor misalignment while transmitting the rotational power from the gearbox to the generator. Watch the coupling installation. The coupling is positioned with the gearbox output shaft on one side and the generator input shaft on the other. The coupling is carefully aligned using alignment measurements and fixtures. Once aligned, the coupling is bolted to the shafts. The alignment must be precise because any significant misalignment will cause vibration and accelerate wear. The rotor assembly, the three blades attached to a hub that connects to the main shaft, will eventually connect to the input side of the gearbox through the low-speed shaft. Before that connection is made, the low-speed shaft is installed in the nacelle, supported by bearings mounted on the frame. The main shaft, the low-speed shaft connecting the rotor to the gearbox, is installed and large bearings at either end supported. These bearings are critical components, capable of supporting the weight of the rotor and resisting the forces transmitted to them when the rotor is operating. The bearings are mounted with precision alignment, using specialized tools to ensure proper positioning. The control electronics are installed in the nacelle. Electronic modules are mounted on racks or frames within the nacelle structure. Cables run from the electronic modules to the various components they control and monitor. The electrical wiring is organized with cable ties and conduits, creating a neat, organized appearance and preventing cables from being damaged by moving parts. The cooling system for the gearbox is installed. Oil coolers and pumps are mounted on or in the nacelle structure. Piping connects the cooler to the gearbox, allowing oil to circulate through the cooler, where heat is transferred to the surrounding air. Temperature sensors in the gearbox provide feedback to the control system, allowing automatic cooling system operation. The power conversion electronics. The converter that converts the variable frequency power from the generator into grid frequency power is installed. This equipment is large and generates considerable heat. Cooling fans or heat sinks ensure that the electronics are properly cooled. The converter is connected electrically to the generator output and to the grid connection equipment. A transformer is often installed in or near the nacelle to step up the voltage from the generator to the voltage required for grid transmission. The transformer is a heavy piece of equipment filled with insulating oil for cooling. The transformer must be properly cooled, often with its own cooling system. The anemometer and wind direction sensor are mounted on the nacelle. These instruments measure the wind speed and direction. The information is provided to the control system to optimize turbine operation. The anemometer is positioned at the top of the nacelle where it can accurately sense the wind arriving at the rotor. The main electrical cable that will eventually carry power from the generator down the tower to the electrical substation is coiled and prepared for later installation. The cable is heavy and requires careful routing to avoid sharp bends that could damage the insulation. Quality control inspections are performed throughout the assembly process. Measurements verify that components are positioned correctly. Electrical tests verify that all circuits are functional and properly connected. The completed nacelle undergoes a comprehensive test before being sent to the installation site. A test run is performed where the nacelle and generator are mechanically driven by an external motor at a slow speed. This verifies that the mechanical alignment is correct, that the gearbox operates smoothly, and that the generator produces electrical power at the correct specifications. Acoustic measurements verify that noise levels are acceptable. Vibration measurements verify that the assembly is balanced and free of significant vibration sources. The completed nacelle is a complex, integrated system of mechanical and electrical components. It represents months of manufacturing and assembly work by specialized technicians. When installed on top of a tower with a rotor attached, it will operate for 20 to 30 years, generating electricity from wind energy. The rotor assembly is the most visually impressive part of the turbine, the massive rotating element that captures the wind's energy. The rotor consists of 3 blades attached to a hub, with the complete assembly weighing hundreds of tons. The rotor hub is a massive steel casting. This is the central piece to which the blades attach. The hub must be incredibly strong because it must transmit the forces of the rotating blades to the main shaft, experiencing stresses of tremendous magnitude during operation. The hub is manufactured from high-strength steel or ductile iron casting, designed to withstand these forces. The hub is manufactured through a specialized casting process. Large molds are created from patterns that define the hub shape. The molds are filled with liquid metal, molten steel or iron, which is cooled and solidified. The casting is then machined to create the precise mounting surfaces and holes where the blades and shaft will be attached. The blade attachment involves large root connections where each blade bolts to the hub. These connection points must be extraordinarily strong because they transmit the full load of the blade and its aerodynamic forces to the hub. Large bolts, perhaps 50 centimeters long and several centimeters in diameter, pass through the blade root and screw into the hub. Watch the blade attachment process. A blade is positioned against the hub. The blade root and the hub mounting surface are aligned. Large bolts are inserted into pre-drilled holes. Workers use impact guns to start the bolts, turning them into place. Then precision torque wrenches are used to tighten each bolt to the exact specification. The tightening sequence is important. The bolts must not all be tightened at once. Instead, they are tightened in a specific pattern that ensures even loading on all bolts and prevents distortion of the connection. The pattern might be like tightening wheel nuts on an automobile, tightening opposite bolts in sequence to ensure even pressure. Each bolt is tightened in multiple passes, with the final pass bringing all bolts to their final specified tension. The measurement of bolt tension is critical. Strain gauges or specialized ultrasonic tools can verify that each bolt is tensioned correctly. Some advanced systems measure the acoustic emissions of each bolt as it is tightened, ensuring that the tension is precisely correct based on acoustic signature. Once all three blades are attached to the hub, the rotor assembly is complete. The rotor is positioned on a support stand, and the main shaft is then installed through the center of the hub. The shaft is supported by the hub and will eventually be supported by the main bearing in the nacelle. The rotor assembly undergoes final inspections and testing. The rotor's balance is checked using specialized equipment. A balanced rotor is critical because any imbalance will cause vibration when the rotor spins. The rotor is suspended and allowed to spin slowly, while sensors measure any vibration. If imbalance is detected, weight is added to or removed from the rotor to achieve proper balance. For large rotors, achieving perfect balance is impossible, but balance is optimized to minimize vibration. Weight is typically added by attaching small lead weights to the hub or to the blades in carefully calculated positions. The weight and center of gravity of the rotor are measured. This information is critical for the turbine installer and for ensuring the tower is adequately sized to support the rotor weight. The rotor is subjected to dynamic testing if possible. The rotor is spun at slow speed using an external motor, allowing observation of how it behaves mechanically. Any unusual vibrations or noises are noted and investigated. The completed rotor assembly is transported to the installation site. The rotor is typically transported on specialized trucks or by ship if offshore installation is planned. The rotor requires careful handling during transport to prevent damage to the blades. Beyond the components installed in the nacelle, a wind turbine requires extensive electrical infrastructure at ground level to handle the power generated by the turbine and interface with the electrical grid. The electrical substation is a separate facility located near the base of the turbine or at a central location if multiple turbines feed power to a common substation. The substation contains transformers, switchgear, circuit breakers, and distribution equipment. The transformer is a large piece of equipment, typically filling a metal tank. The electrical substation is a separate facility located near the base of the turbine or at a central location if multiple turbines feed power to a common substation. The substation contains transformers, switchgear, circuit breakers, and distribution equipment. The transformer is a large piece of equipment, typically filling a metal tank perhaps 3 meters long and 2 meters tall. Inside the tank, copper windings and iron core create the transformer that will step up the turbine voltage to a higher voltage suitable for transmission to the power grid. Transformer manufacturing is itself a specialized process. Copper wire is wound around an iron core in precise patterns, creating primary and secondary windings. The number of turns in each winding determines the voltage transformation ratio. The windings are insulated from each other and from the iron core using special insulating paper or other materials. The completed winding assembly is placed in the transformer tank. The tank is filled with transformer oil. a specialized mineral oil that provides electrical insulation and cooling. The oil surrounds the windings, providing cooling and preventing air from contacting the windings, which would cause oxidation and failure. Bushings are installed where the electrical leads exit the transformer tank. These ceramic and metal assemblies provide electrical insulation while allowing wires to connect from the windings to external circuits. The bushings must be capable of handling the high voltages present in the transformer. The transformer is tested before being placed in service. High voltage tests verify that the insulation is adequate. Tests of the oil verify that it has the proper dielectric strength and is free of moisture or contamination. Turns ratio testing verifies that the windings have the correct number of turns for the desired voltage transformation. Circuit breakers are electrical switches designed to automatically interrupt electrical circuit if dangerous conditions develop. Overcurrent breakers open the circuit if current exceeds safe limits, protecting equipment from overload. Overvoltage protection devices prevent voltage from exceeding safe limits. Ground fault protection devices detect unwanted current flowing to ground and trip the breaker to prevent danger. Watch the circuit breaker operation. The breaker is a sophisticated electromechanical device containing multiple components. When normal current flows, contacts remain closed and current passes through. If a fault condition is detected, excessive current, excessive voltage, or ground fault, the protection system commands the breaker contacts to open. The contacts separate, interrupting the circuit, and the electrical arc created by the separation is quenched in specialized arc quenching chambers, preventing damage to the breaker. Disconnects and switches are positioned to allow isolation of components for maintenance. Grounding equipment ensures that any stray current has a safe path to ground. Cable routing is planned and labeled to avoid confusion and ensure proper operation. The substation control system uses computerized controllers to manage the electrical flow. These controllers monitor power flow, voltage, frequency, and other parameters. If the wind turbine output exceeds the capacity of the grid, or if grid voltage or frequency becomes unstable, the control system can disconnect the turbine from the grid to protect the grid and the turbine. Communication systems connect the substation control system to the turbine control system and to the central control facility. Data about power generation, voltage, current, and fault conditions is transmitted from the turbine to the control center where it is monitored and analyzed. Protective grounding systems are installed to ensure safety. Every metallic component in the electrical system is grounded. Copper conductors run from every potential hazardous point to ground rods driven deep into the earth. If a fault occurs, the current follows the grounding system to earth, minimizing the risk of electric shock to workers. The electrical cable connecting the turbine to the substation is a major component. This cable must carry the full electrical current from the turbine generator to the transformer. For a large turbine generating 15 megawatts, the current might be several thousand amperes. The cable must be large in diameter to minimize resistive losses and heat generation. The cable is manufactured by cable makers who extrude insulation around the copper or aluminum conductor. 4 high-voltage cables, multiple layers of insulation are used. The outermost layer is typically a tough protective jacket that resists mechanical damage, weathering, and UV radiation. The cable is installed in conduits buried underground or suspended on poles from the tower to the substation. The installation must protect the cable from damage and environmental exposure. Cable pulling is performed by mechanical equipment to avoid exceeding maximum pulling tension that could damage the cable insulation. Testing of the electrical system is extensive. Insulation resistance testing verifies that the electrical insulation is not damaged or degraded. HIPAT testing applies high voltage to verify insulation adequacy. Load testing verifies that all components function properly when full electrical load is applied. Safety testing verifies that protective systems function correctly. Tests simulate various fault conditions: overload, overvoltage, ground fault, and verify that protection systems operate correctly to disconnect power when needed. All the manufactured components must be transported to the installation site and assembled into the complete turbine. The tower assembly is a critical phase where the separate tower sections are joined together. The tower sections are transported to the site by truck. Each section requires specialized transportation equipment. The sections are typically transported horizontally on the truck beds, their length extending beyond the truck. Special permits are required for transport of such large structures. At the installation site, the foundation has been prepared in advance. A large concrete foundation anchors the base of the tower. Anchor bolts embedded in the concrete will fasten the tower base. The foundation extends deep into the ground to ensure stability and to resist the overturning forces that wind pressure on the tall tower will create. The first tower section, the base section, is positioned vertically over the anchor bolts. A large crane lifts the section and positions it. The anchor holes in the tower base are aligned with the anchor bolts in the foundation. The alignment must be precise. The holes must align properly or the section cannot be secured. Large anchor bolts are inserted through the holes and tightened. These bolts are enormous, perhaps 5 centimeters in diameter, and are tightened to tremendous tension. Hydraulic torque wrenches apply the specified tightening torque, ensuring each bolt has the correct tension. Watch the bolt tightening process in detail. The hydraulic wrench is positioned on the bolt. The pump starts, applying hydraulic pressure to drive the wrench. The bolt slowly tightens. The gauge on the torque wrench shows the applied torque. When the correct torque is reached, the pump automatically stops. The wrench is removed and the next bolt is tightened. The process continues, bolt by bolt, until all anchor bolts are properly secured. Once the first section is secured, the second section is positioned on top of it. The upper flange of the first section and the lower flange of the second section are carefully aligned. Large bolts join the two sections, creating the tower joint. The flange joint is particularly important because it must transmit all the forces between the tower sections. The bolt connection must be very strong and properly aligned. The bolts are distributed around the circumference of the flange, typically numbering perhaps 40 or more large bolts per joint. The bolts are tightened in a specific sequence, typically in a cross pattern to ensure even loading and proper joint alignment. The tightening is performed in multiple passes. The first pass brings all bolts to approximately half their final tension. The second and third passes incrementally increase the tension until the final specification is reached. Instrumented bolts may be used in critical joints. These bolts include strain gauges that electronically measure the bolt tension. The gauge reading ensures that the bolt is tensioned exactly correctly. This measurement capability is valuable for ensuring consistent joint quality. Additional tower sections are added in sequence, each one carefully positioned, aligned, and bolted to the previous section. The tower grows taller with each addition. As the tower becomes taller, the installation becomes more challenging. Working at height creates safety considerations, and the increasing height magnifies any alignment errors. Safety systems are critical during tower assembly. Workers are protected by fall protection equipment. Harnesses and lanyards attach workers to the tower, preventing falls if they lose their footing. Work platforms and temporary scaffolding provide safe working areas. When all tower sections are assembled and bolted together, the complete tower stands ready to support the nacelle and rotor. The tower is verified to be vertical using laser levels or clinometer measurements. Any deviation from vertical is noted and corrected if necessary. The electrical cable that will connect the generator to the substation is installed inside the tower. The cable runs through the interior of the tower, protected from external weather and mechanical damage. Cable hangers support the cable at intervals, preventing excessive sag. Access ladders and platforms are installed inside the tower to allow personnel to climb the tower for maintenance. These are safety features allowing workers to reach equipment inside the tower for inspection and repair. With the tower complete and standing vertically, the nacelle, the generator unit containing the gearbox, generator, and controls, must be lifted to the top of the tower and installed. This is a critical and complex operation requiring specialized equipment and careful coordination. A large crane is positioned near the tower. This is not a small crane. Lifting the nacelle might require a crane capable of handling hundreds of tons. The crane is positioned carefully, its location verified to ensure stability and proper positioning. The nacelle is positioned on the crane hook using specially designed sling equipment. The slings distribute the load evenly, preventing damage to the nacelle structure. Multiple slings are used, typically at least 4, to ensure that the nacelle cannot tilt or rotate unexpectedly during the lift. Watch as the crane begins to lift the nacelle. The hook rises and the nacelle is lifted slowly and deliberately. The load must be raised slowly to allow for any adjustments if the nacelle begins to tilt or rotate. Workers on the ground monitor the lift, ready to alert the crane operator of any problems. As the nacelle rises toward the tower top, it must be guided into the correct orientation and position. This is not a simple task. The nacelle is large and difficult to see from the ground. Spotters, workers positioned to see the nacelle, communicate with the crane operator by radio, providing directions to position the nacelle correctly. Left a little, down a little, hold it there. The communications continue until the nacelle is exactly above the tower opening. The nacelle is lowered slowly until it seats on mounting equipment at the top of the tower. Large guides and alignment pins help position the nacelle correctly on the mounting points. The nacelle must be positioned precisely so that all mounting bolts align with their holes and so that the main shaft aligns with the rotor that will be attached next. Once the nacelle is properly positioned on the tower, it is secured with large bolts that are tightened to specified torque. These bolts are critical. They must hold the nacelle securely in place despite the enormous forces it will experience when the rotor is turning and wind forces are acting on the turbine. The electrical connections are now made between the nacelle and the tower interior. The main power cable from the generator is connected to the cable that runs down the inside of the tower. This is high voltage, high current work that must be performed with great care to ensure proper connections and safety. Control signal cables are connected from the control systems in the nacelle to control equipment elsewhere in the system. These cables carry the control signals that coordinate turbine operation. With the nacelle securely installed, the rotor can now be installed. The rotor is transported to the site on specialized trucks and is positioned on a support structure near the tower. The rotor, consisting of the 3 blades and hub joined together, must now be lifted to the top of the tower and connected to the main shaft. This is perhaps the most dramatic installation operation. The rotor, weighing hundreds of tons, is lifted by crane to the top of the tower. The lift requires a very large crane, often a specialized heavy lift crane. The load is enormous and the coordination required is complex. The rotor is lifted slowly and carefully. Spotters monitor the lift, ensuring proper alignment as the rotor rises. The rotor must be oriented correctly. The blades must be positioned appropriately to avoid catching on the nacelle or tower during the positioning operation. As the rotor nears the top of the tower, it must be aligned with the main shaft that extends from the nacelle. The main shaft has a hub on the end that mates with the rotor hub. The alignment must be precise. The two hubs must mate properly for the spline connection to work correctly. Slowly, the rotor is lowered onto the main shaft. The two hubs come closer together. When contact is made, the splines must align to allow the rotor to settle onto the shaft. If alignment is off, the rotor cannot be seated. Spotters guide the final positioning, ensuring that the rotor seats properly on the shaft. Once the rotor is properly seated, large nuts are installed on the shaft and tightened to secure the rotor. These nuts are tightened to tremendous force, creating a connection between the main shaft and the rotor that will not separate despite the enormous centrifugal forces the rotor will experience during operation. Finally, the rotor should be rotated slowly by hand or by powered equipment to verify that it rotates smoothly without binding or resistance. This verification ensures that the mechanical alignment is correct. With the mechanical installation complete, the electrical systems must be tested and verified to function correctly. The turbine is now mechanically complete, but electrical integration and testing ensure that all systems work properly together. The main transformer in the substation is tested and energized. Tests verify that the transformer is operating at correct voltage and frequency. Metering equipment measures the electrical characteristics and verifies that everything is within specification. The turbine generator is tested. Specialized test equipment verifies that the generator produces electrical power at the correct voltage, frequency, and phase. The generator is spun slowly by an external motor while measurements are taken to verify proper electrical performance. If the wind turbine is being tested near synchronous conditions with the grid, the output frequency is precisely matched to the grid frequency before any connection is made. The power converter electronics, the equipment that converts the variable frequency power from the generator into fixed frequency grid power, is tested. The converter is run through a range of operating points to verify that it functions correctly. Electrical losses in the converter are measured. Harmonic distortion is measured to verify that the converter output meets grid connection standards. All electrical protective devices are tested. Overcurrent relays are tested with injected current signals to verify that they trip at correct current levels. Overvoltage and undervoltage protection is tested. Ground fault protection is tested. Phase rotation protection, frequency protection, and all other protection systems are verified to function correctly. Communication systems are tested. Signals are transmitted from turbine to control center and back, verifying that communications are reliable. Data acquisition systems are verified to correctly collect and transmit turbine operating data. The control system software is tested extensively. The software is installed on the control computers, and test programs verify that it functions correctly. Fault injection testing simulates various fault conditions to verify that the control system responds appropriately. The safety systems are tested. Emergency shutdown systems are tested to verify that they can rapidly stop the turbine if needed. Load shedding systems. Systems designed to reduce the turbine load if the grid becomes unstable, are tested. Watch as technicians perform these tests. They are seated at computer stations, monitoring test parameters displayed on screens. Data is displayed showing voltage, current, frequency, and other parameters. As test conditions are changed, the technicians observe how the system responds, comparing the measured values to expected values. If discrepancies are found, troubleshooting procedures identify the cause and corrections are made. Environmental conditions in and around the turbine are monitored. Temperature sensors in the gearbox and generator verify that these critical components are operating at safe temperatures. Vibration sensors throughout the turbine measure vibration and verify that vibration levels are acceptable. If the turbine is expected to operate in high wind conditions, wind simulation testing may be performed. The control system software is tested with simulated wind speed signals to verify that the blade pitch control system responds correctly to varying wind speeds. The nacelle anemometer and wind direction sensor are tested and calibrated. These sensors provide inputs to the control system to optimize turbine performance based on wind conditions. Calibration ensures that the sensors provide accurate measurements. Once all electrical systems and controls are tested and verified, the turbine is ready for field testing, low-speed rotation testing before it is connected to the grid and begins generating electricity for real use. Before the turbine is permitted to feed power to the electrical grid, it must be thoroughly tested in the field to verify that all systems function correctly under real operating conditions. The turbine is energized and prepared for initial testing. The first test is simple. The rotor is rotated very slowly at perhaps 1 or 2 revolutions per minute to verify that everything rotates smoothly without binding or excessive resistance. Personnel listen and observe for any unusual sounds or vibrations that might indicate mechanical problems. The turbine is allowed to idle in light wind without producing electrical power. The control system monitors wind speed and blade pitch, responding to changing wind conditions. Operators observe how the turbine responds, verifying that the control system adjusts blade pitch correctly to maintain stable operation. Gradually, wind conditions allow the turbine to accelerate to higher speeds. As wind speed increases, the turbine accelerates. At a certain wind speed called the cut-in speed, perhaps 3 to 4 meters per second, the turbine begins to generate electrical power. The power output is initially small, but as wind speed increases further, the power output increases. Watch the power curve, the relationship between wind speed and power output. At low wind speeds, there is insufficient power to generate electricity. As wind speed increases, power output increases dramatically. At higher wind speeds, the blade pitch control system adjusts the blade angle to limit the power output, preventing the turbine from overloading. At the rated power wind speed, perhaps 12 to 14 meters per second, the turbine generates its full rated power. At this point, further increases in wind speed do not increase power output because the blade pitch adjustment prevents additional power from being generated. At very high wind speeds, the turbine must be protected by shutting down. A wind speed called cutout speed, perhaps 20 to 25 meters per second, triggers the turbine to automatically shut down. The blades are rotated to an angle that creates no lift, and the rotor slows to a stop. All of this automatic control is tested. The testing verifies that blade pitch control responds properly to wind speed changes, that power ramping is smooth without sudden surges or drops, and that the turbine safely shuts down at high wind speeds. Electrical output is measured under various wind conditions. The voltage, current, frequency, and phase of the output power are measured and verified to meet grid connection standards. Power factor, the relationship between real power and reactive power, is measured and verified to be acceptable. Harmonics are measured. Modern wind turbine power converters generate minimal harmonics, but testing verifies that harmonic distortion is within acceptable limits. If harmonics exceed limits, converter operation is adjusted or filters are installed to bring the harmonics within acceptable levels. Grid compatibility is verified. The turbine is connected to the grid through protective disconnect switches. The grid connection is momentarily closed. The turbine begins feeding power into the grid, and all parameters are monitored. Protective relays verify that normal connection has occurred. The connection is then immediately opened to end the test. This is repeated several times, confirming reliable grid connection and disconnection. Once grid connection is successful, the turbine may be allowed to remain connected and continuously feed power to the grid. The turbine operates under the control of the automatic control system, responding to changing wind conditions and maintaining proper power output. Extensive monitoring is performed during the initial period of operation. Data is continuously recorded from hundreds of sensors throughout the turbine. Power output is recorded. Wind speed and direction are recorded. Vibration and temperature are recorded. Electrical parameters are recorded. All this data provides a complete picture of how the turbine is performing. After sufficient operating hours, typically hundreds to thousands of hours, the accumulated performance data is analyzed. Power output is compared to expected values based on wind speed data. If performance is as expected, the turbine receives final certification and is accepted as fully operational. Minor adjustments and repairs may be needed based on the initial operating experience. Perhaps a vibration source is identified and corrected. Perhaps software is fine-tuned to optimize performance. These adjustments are made and the turbine continues operating. The turbine is now fully operational, feeding clean electricity to the grid. The manufacturing and installation project is complete. The turbine will now operate for 20 to 30 years, generating electricity from the wind and contributing to a sustainable energy future. Once a wind turbine is operational, ongoing maintenance is required to ensure continued reliable performance. The maintenance is performed by specialized technicians trained in wind turbine service. Regular inspections are performed at scheduled intervals. Technicians climb the tower to the nacelle carrying tools and equipment. The inspection typically occurs every 6 to 12 months, depending on turbine manufacturer recommendations and operating experience. Watch the inspection process. The technician makes the long climb up the access ladder inside the tower, rising hundreds of meters. Reaching the nacelle, the technician performs a visual inspection, checking for any obvious signs of wear, damage, corrosion, or other problems. The technician inspects the blades from the nacelle, looking at the blade surfaces for any signs of erosion, damage, or delamination. Oil samples are extracted from the gearbox and analyzed. The oil analysis reveals where in the gearbox, particles of iron and steel in the oil indicate gear or bearing wear. The analysis determines if oil condition is acceptable or if the oil should be changed. The analysis might also reveal developing problems such as copper wear indicating bearing damage. Electrical systems are tested. The generator insulation resistance is measured using a megometer. Electrical connections are inspected for corrosion or looseness. Control system operation is verified by exercising the control functions and observing the turbine response. Bearing temperatures are monitored continuously by temperature sensors. Bearing temperatures provide an early indication of bearing problems. Elevated bearing temperatures might indicate increased friction caused by bearing wear, inadequate lubrication, or contamination. If bearing temperature rises abnormally, the turbine can be shut down before bearing failure occurs. Vibration monitoring is performed using accelerometers that measure vibration at critical locations. The vibration signature changes if problems develop. Increased vibration might indicate gearbox wear, bearing damage, or blade imbalance. Vibration monitoring systems can alert technicians to problems before catastrophic failure. Blade surface erosion is monitored. The leading edges of the blades gradually erode in service as rain, dust, and ice particles impact them. The erosion gradually reduces the aerodynamic efficiency of the blades. If erosion becomes severe, blade repairs or coatings may be applied to restore efficiency. Electrical connection tightness is periodically verified. The large bolts that join tower sections and the bolts that fasten the nacelle to the tower are rechecked to ensure they remain tight. Environmental stresses and vibration can gradually loosen bolts if not properly maintained. Software updates are periodically applied to the turbine control system. Updates may improve turbine performance, improve reliability, or correct identified problems. The updates are loaded into the control computers, and the system is tested to verify proper operation. Filter changes are performed at regular intervals. Air filters and coolers and cooling equipment are changed to maintain cooling efficiency. Hydraulic filters and hydraulic systems are changed to maintain fluid cleanliness. Fuel filters, if the turbine has backup diesel generators, are changed regularly. Corrosion protection is maintained. The exposed painted surfaces of the turbine are inspected and touch-up painting is performed to prevent rust. The electrical connectors are inspected and cleaned to maintain proper electrical connections. When major components approach the end of their service life, they are replaced. Gearbox replacement might occur after 15 to 20 years if bearing wear becomes excessive. Generator replacement might be needed if winding insulation degrades. Control system computers might be upgraded with newer technology. Modern condition monitoring systems continuously transmit health data from the turbine to remote monitoring centers. Specialists review this data to identify emerging problems. Predictive maintenance uses this data to schedule repairs before failures occur, reducing downtime and repair costs. The completed wind turbine, from manufacturing through commissioning to ongoing operation, represents one of the engineering marvels of our time. Modern wind turbines convert invisible wind energy into electricity with remarkable efficiency. Thousands of these turbines operate worldwide, contributing significantly to renewable electricity generation. A modern wind turbine is far more than a simple machine that the wind turns. It is a marvel of engineering integration, combining mechanical, electrical, and control systems to reliably convert wind energy to electricity at a scale that contributes meaningfully to global electricity generation. The design process required sophisticated engineering analysis using computational tools that did not exist a few decades ago. The manufacturing process employed precision machining and assembly techniques that have been refined over centuries of industrial development. The installation process required specialized equipment and careful coordination of teams of workers. The testing and commissioning process ensured that every system functions correctly and safely. Thousands of people contributed to the manufacturing and installation of this single turbine. Engineers designed every component. Machinists operated precision machine tools. Welders created strong bonds between steel parts. Assembly workers coordinated multiple components into complex systems. Electrical technicians installed and tested electrical systems. Installation crews lifted massive structures and carefully positioned them. Inspectors verified quality throughout the process. The design knowledge embedded in a wind turbine represents centuries of engineering advancement. Aerodynamic principles understood through wind tunnel testing and computational analysis guide blade design. Mechanical engineering principles guide gearbox and bearing design. Materials science provides understanding of the properties of steel, composite materials, and other materials used in the turbine. Electrical engineering principles guide the generator and power electronics design. Control systems theory guides the automation and control system design. The wind turbine will operate for 20 to 30 years, generating electricity reliably and automatically. It will generate electricity during daylight hours and at night, during calm conditions and windy conditions throughout the seasons. The electricity will power homes, businesses, and industries. The renewable energy it generates displaces electricity that would have been generated using fossil fuels, reducing greenhouse gas emissions and contributing to a sustainable energy future. The reliability of modern wind turbines is remarkable. Despite the enormous forces and environmental stresses they experience, well-maintained turbines operate with high availability, perhaps 95% or higher. This reliability is the result of careful design, quality manufacturing, and diligent maintenance. The economics of wind energy have improved dramatically in recent decades. The cost of electricity generated by wind turbines has decreased significantly, making wind-generated electricity competitive with electricity from conventional power sources in many locations. The improvements in turbine efficiency and manufacturing processes continue, making wind energy increasingly cost-effective. The environmental benefits of wind turbines extend beyond the electricity they generate. Wind turbines create no pollution during operation. They require no water for cooling. They generate no radioactive waste. They can be integrated into agricultural land, coexisting with farming activities. The turbine we observed in this video is one of thousands operating worldwide. Collectively, these turbines generate tens of thousands of megawatts of electricity, providing a significant percentage of global electricity generation and an increasing percentage in many countries. The manufacturing, installation, and operation of wind turbines represents one of humanity's responses to climate change and energy sustainability challenges. As technology continues to advance and costs continue to decrease, wind energy will play an increasingly important role in providing clean electricity for future generations. Thank you for joining us on this journey through wind turbine manufacturing and installation. We hope you have gained appreciation for the complexity, precision, and ingenuity required to create these remarkable machines that harness the power of the wind.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark. Me fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still scene.